Russell, and I'm here to tell you about isotopes and percent abundance. This is a PHET simulation, and I'll post the link to this simulation with the video. So when I look at the helium-4 isotope, I'm looking at this thing right here where it says helium-4. That means that there are four nucleons, if you will. That those nucleons are the four items in the nucleus. So that they could be either protons or neutrons. Protons with a positive charge, neutrons with no charge at all. The only thing neutrons bring to the table is their mass. So we'll see the mass change when we take a neutron away. See that the mass number went down, and now it's the helium-3 isotope. So the definition of an isotope is the difference is something with the same number of protons but different numbers of neutrons. This is the hyphen notation where we have helium-4, meaning that the mass number is 4, but you might also see it in nuclear notation here where it has the element symbol helium and a 4 here on the in the top left corner. The 2 on the bottom is the atomic number, which is the number of protons. That will if it's helium, that will always be a 2. Always, always, always. So if I move to the helium-3, this is still a 2. So now these don't happen in nature equally. 99.99999% of the time, helium-4 will be the one that exists. But very rarely, sometimes we can get the helium-3 isotope. These are both stable. Now, if I add an extra neutron, it might be unstable. So if I take it away, now I can get that back stable again. If it's unstable, that means that the nucleus is just getting too big for it to hold. So it will actually eject that neutron in what we call radioactive decay. Another way to show this is if I take, I'm going to make my picture smaller. If I take something like this, and if I take the hydrogen isotope, the 2 stable isotopes that exist, if I take these and I can just make my own little mixture and putting the hydrogen 1 isotopes here and the hydrogen 2 isotopes here. I can put them anywhere I want. And if I add more of these, the percent abundance is shown right here in this little pie chart, and also a percentage here. That means that if this is my whole universe or my whole sample size, that means that 77.8%, well, let's make that an even number, 75% of these hydrogens are hydrogen 1s, and 25% of them are hydrogen 2. So you can move around with these. Sometimes with oxygen, you'll have 3 different isotopes that are available. And if they're, but this is, let me be stressed to you, this is just my mixture. If we take a look at what nature's mixture looks like, we notice that very rarely does the hydrogen 2 isotope exist. But if we look at oxygen, the oxygen 16 definitely does reign supreme. Oxygen 18 might show up, and then oxygen 17 even less. And that's where we get these percent compositions. To calculate average atomic mass, we need to know 2 things. We need to know the isotope that we're dealing with, but we also need to know the percent abundance. These percent abundance values will be given to you always. There's no need to ever memorize them. And also, I will tell you the I will tell you the isotopes that you'll be working with. So I have three isotopes of carbon, carbon-12, carbon-13, and carbon-14. I threw carbon-14 in here to show you that sometimes we may have something that is radioactive and it is not stable, so it does not have a percent natural abundance. That's why the 0% is there. So if we were to calculate the average atomic mass, we need to know the average of these masses, but we also need to take into account the percent abundance. This one will occur, carbon-12 will occur more often than carbon-13. So to do this, we will take the mass number and multiply it by the percent value. I've changed the percents here from a percent to a decimal place. I divided it by 100, or I moved the decimal places 2 places to the left. See how I did that? So and then I added to my next term, which is carbon-13, multiplied by my percent value. And then if I went ahead and threw in the next term, which is 14 times 0, which we know will be 0. This will, once I type the entire thing into the calculator, it will give me 12.01, and my units are AMU. A quick check, the average mass should be close to the one that's on the periodic table, if not exact. This is the exact mass that you would see on the periodic table. A couple of things to watch out for. Make sure you change the percents to decimals, or else your math won't work out right. Also, make sure you don't round until the very end. If you do this calculation and round, and then do this calculation and round, and then add two rounded numbers together, you may get an incorrect answer. The average atomic mass is the weighted average based on isotopic composition. To calculate, take the percent isotope A times the mass of isotope A, plus the percent of isotope B, plus the mass of isotope B, plus, and then we go on for all the terms that we have. That will equal the average atomic mass. So here's another example. What is the average atomic mass in grams of lithium if 7.42% exists as lithium-6, which has a molar mass of 6.015, and 92.58% exists as lithium-7, has a molar mass of 7.016 grams per mole. I will take my percent values and multiply by my mass that's given here. The only difference between the example before is before I use the whole number 6, but if I give a more specific answer, you want to use that one. That one's a better calculation to get. And then I will add it to my next term, which is my percent, 0.2958, which is the same as 92.58%, times 7.016. So again, instead of lithium-7, I put 7.016 grams per mole. And the answer will be 6.94. So check the periodic table, look for lithium. Is it close to 6.94? If it is, you are right. You know you have the right answer. Don't forget these things at the bottom. Don't forget to round until the end. A mass spectrometer is an instrument that we can use to help us understand the percent abundance of different isotopes. We take advantage of the only difference between different isotopes. Since they all behave chemically, the only way to separate them is by mass. So we will, if the sample is not already a gas, we'll have to heat it in a vaporizing device like a heating coil, and it will first pass through an electron beam. This electron beam will actually pull the electrons away. Um, it sounds counterintuitive, but it'll actually pull those electrons away so that we have positive charges on our sample. So, and now the sample will be accelerated through the slits, and so that they're all moving the same speed. The next thing it will pass through is the magnetic field. This magnetic field is specially calibrated for this sample, and it has to be calibrated every different times. And as it moves through, the lighter ones will get deflected the most because if you think of a ping pong ball, it's easier to push a ping pong ball than it is to push a pool ball because the ping pong ball is so much lighter, right? So the lighter ones will actually get deflected the most, and the heaviest ones will get deflected the least. So the lighter ones will travel up and come and hit this detector here in a different place than the heavier ones, which will hit the detector here. I'll point out that they keep the temperature, the electron beam, and the speed at which the ions are traveling all constant, always constant. The only thing that they'll change is the magnetic field. We can actually measure how much we take advantage of the fact that we can measure how much electricity is being applied to that magnetic field, and that's what we're actually measuring when we calibrate it. Whenever we take our independent variable, our dependent variable, sorry, that is going to be what hits the detector plate. So our independent variable would be the electrical charge in the magnetic field, and the dependent variable, what we expect to receive, is going to be what's on the detector plate, the different places that it will show up. This is an example of a spectrum that we'll get. We notice that this part of the detector plate was struck more often. It was struck 69.09% of the time, and this part of the detector plate was struck 30.91% of the time. So we find out that in this sample of copper, the mass number of copper will be 63. Now notice that this is not the atomic number of copper. So when you look at these peaks, you might see 63 and look for number 63 on the periodic table and find something, and I don't know what that is, but it's not copper. Remember, this is the mass number. This is the protons plus the neutrons. So the good way to guess what it is, you need to just divide by 2. And that will be, that's a pretty good ballpark answer, which element it is. So if we look at the figure for neon gas, one way that we could see this is we're getting some background noise when we get something like this. Instead of showing individual peaks, we'll get these peaks right here. So you might be able to see some background noise, but you really want to focus on the peaks. This only gives us the X value, and it doesn't give us a Y value, so this graph isn't very helpful. But this graph, which is of the same data, is also very helpful. We can see that there's 91%, 0.3%, and 9%. So you may have noticed that in the previous slide, those relative abundances, abundanci, did not actually add up to 100. They add up to 100.3. So the way we need to handle this is we need to kind of get them back down to 100. So I will then take each one and divide it by the total. My total is now 100.3, and I'll get 90.73%, and I'll get 0.29% and 8.9%. Hey, look, it's right there. So now when I do the correct values, I will take these percentages and multiply them by my mass numbers. Here's the percentage, here's the mass number, and then that's my first term, and then the percentage and mass number of my second term, percentage and mass number of my third term. That will equal about, with 4 significant figures, let's just give 2 decimal places, and we'll get 20.16. Just to show you the incorrect way, let me move my head. The incorrect way would, if we did it with the alternate ones, if we calculated it out, it would be 20.24. Close, but not enough to make a difference. Okay? Another test question you might get asked is something like this, where what element results in this mass spec data? I can see over on the top left, over there, it says relative abundance, and down here is the mass number, right, in AMUs. So I can see across the bottom where it's showing 196, 198, 199, all those. So I know that my range is somewhere between 196 and 204. It's probably somewhere around 200, right? So estimate somewhere around 200. You need to go to the periodic table. Here, you want to look at these bottom numbers. Those are the atomic masses, right? The periodic table for Mercury is going to be exactly 200.59. See it? It's right there. Do you see Mercury? You can see if you move a little bit to the left, you get 196, and it's clearly not right. And if you move a little bit to the right, it's going to be 204. So that's also not right. So the answer I would choose is Mercury. Please notice that this is not the atomic number. You would not look at the atomic number around 200, okay? Because that would be way wrong. You want to look at the mass number. Hey, thanks for watching, guys. Make sure that you wrote everything down in your composition book so that you have all your notes with you. When you come to class, we're actually going to do a group activity with this mass spec data. So make sure you're prepared. Thanks.